Thank you very much for coming. I'm Syed from Web3 Foundation, and this is a work with Alistair. It's mostly Alistair's work. I read it and I implemented it, so I get to be here. But so let us start. And there's quite a lot of material packed here. Because it's a workshop, I didn't want to jump just to like conclusion and stuff. I thought I will explain the background, but I can't go slow on it because then we don't arrive to the end. So I'll try to go over the background so you hear all the theory behind this stuff. On the other hand, you could stop me. So if something that you have a question, you stop me, you ask. I'm happy it's a workshop, right? And I hope to get to look at some of the code and implementation of the stuff, so it's not only abstract object that we are going through. But let's start, okay? So motivation. So yeah, I hope make you more excited about it. We'd like to do Plonk. Like Plonk is very popular. Mostly it's simple, it's probably the simplest snark somebody can explain to people. Like in the courses, like if you want to teach a snark to somebody at the beginning, I think Plonk is the one that they can much easier than the other system get a hold on. Is extendable, you can do Plonkish, basically. You can change the gate and then make it even better. So you learn the system, so it's pretty good. And unfortunately, we have this problem. I mean, a lot of the other systems have the same problem, right? So we only can work in fields that 2 to power, there's a root of unity of a 2 to some big power, yeah, that is in that field. And if you don't have it, then you are doomed, basically. So people say, so what? Like, I'm going to choose a field that has this property. Why do we care? Sometimes you don't get to choose. That's the problem. The field that you're going to work on is coming from the problem underneath, and it just, you have to deal with it. So in those cases, for example, like we have this algorithm, Web3 sum for adding, verifying the addition of the public keys together. This public key is coming from an elliptic curve, which are defined over a finite field already. And you don't get to choose to do it in another finite field because already in that finite field, and it might happen that that finite field doesn't have that property. Now, if you want to do Plonk, then you have the same problem. Or if you do recursive snark, you get the same problems because you do it in the first field, then it comes in the second field. Now the field is changed. You don't have a lot of freedom to choose these curves that shows up there. So there is a lot of example of that. That is why people write non-native snarks, because their field doesn't work. They may move it somewhere else, but non-native snark gives you 100 times more cost to the computation. So they are not the best solution if you can find another solution for it. Oh, sorry. Okay. So to solve this problem, we try to hack something that works with it. This is a work built on ECFFT paper and then ECFFT2 paper, which never got published. But so we took those works and then we adapted them to Plonk, and we made it to solve this problem. And the fun part of it is it touches so many branches of the math. So it's just an introduction to the math that is used in ZK, that's actually just an interesting problem for you to go through it. Okay. I'm going to just go over Plonk, because if you don't have it in your mind, then I'm talking about, I'm referring to stuff that's people don't have a touch, but I will go very fast over it. But I'm doing this because we want to see what is Plonk, to see what problem we need to address to move it to another place, because we are not going to use that field, which is not good. We have to move it somewhere else. Going through the step of Plonk, we see this new place should satisfy which criteria. Then I will go fast over what is FFT, because we are going to talk about it a lot. And then if you doesn't have it in the mind, then you will be lost. We talk a bit about elliptic curve and isogenies, because these are being used in the ECFFT algorithm, but not very deep into them, but just to mention them so they are not just foreign words. Then we talk about ECFFT algorithm, which our work is based on. And we have implementation of it to look like how we work with this actual stuff that they're actually working, because it gets too many complicated objects, but finally using Sage, you can implement it. I will show you this. And then finally, I'll talk about our solution, which basically we want to move Plonk to the coordinate ring of elliptic curve instead of doing it in the field. And this is much more diverse object that you always can find something good in a form of an elliptic curve coordinate ring instead of a field that is dictated to you, and then you don't have that good property, and then you're doomed. You have no other choice. Here you can change your elliptic curve and get a better object. So we are going to talk about that. And then these are not nice. These are not as nice as fields, right? Fields are very nice. Everything is invertible, and the polynomial ring over the field then is everything is factorizable. Everything these lack some of those property, but we still manage to do it. But we go through the thing that we have to hack basically to make it work. And at the end, we go over one small example just for you to look how it works. Okay, so I'm going fast over this. So Plonk, okay? So we start from a circuit, then we look at the arithmetization of the gates and the zero test. Then we look at the wiring arithmetization. This is the basically Plonk part of the Plonk. The permutation of the P is coming from that, and that is the complicator of the Plonk. And that makes the problem part of this thing is mostly coming from there, problematic part. And then basically we talk in abstract. If I want a mathematical structure that I can run Plonk on it, what property that should have. Okay, so I'm taking this from Plonk by hand example. So it's Pythagoras. I want to prove that I have a solution to Pythagoras problem, right? So I want to prove I have x1, x2, x3 that's satisfy the Pythagoras equation. Is not full, right? I can satisfy with 0, 0, 0, with 0, 1, 0, with 0, 1, 1, So it's not a real answer, but I don't want to add more criteria. I just want to have 4 criteria because my big power is 4. So I can't really go over that because in that example. So I go just with these 4 criteria, and then I'll generate a polynomial which will make the problem. So we start with this problem. These are my criteria, right? 3 of them are multiplication, and 1 of them is addition. So that is how Plonk works, right? This is the big equation of Plonk that's encapsulate all the conditions, except you can change it, right? That is the beauty of Plonk. You can take this off and you say my gate is basically customized in a way that make my problem faster. But the basic gate is there. So it allows you to add A and B, right? And have a result, and it also allows you to multiply them and have a constant. So QL means that you are adding A, QR means you are adding B, QO means that you have output, the output is not 0, QM means that you're multiplying A and B together, and QC means you have a constant. So basically here I say, in the first criteria, I am not adding anything, so I put 0, 0, right? And then here, I have output and I have multiplication, which they add together, they should give me 0. So using that, I can just translate this to the Plonk language, right? So, and then what I'm going to do here, in normal Plonk, you would use root of unity here, but if you don't have it, then what are you going to do, right? So we are going to see what we are going to do that. For now, I call them H1, H2, H3, H4. But abstractly, this is the setting. So next step, what I'm going to do, I'm going to interpolate a lot of polynomials. I would say, let me go to the next slide. I would say, okay, I want to find a polynomial QL, which at this object, H1, is 0, which is root of unity in a classic Plonk. First root of unity is 0, 0, 0, and 1. And then I will interpolate, and I get a polynomial, which represent this thing. And I do that for every other column. So I interpolate all the columns. And then I will add them together in the way that the gate was. And I get this huge polynomial, which is interpolation of all these together. And then this polynomial should be 0 at all these, right? That is how the verifier will verify that you have actually the polynomial. It says, give me the polynomial at 0 at all these places. So basically, that is the first thing I did here. I did interpolation. So if I don't have a good interpolation, then I'm doomed. So I need a good interpolation. The good interpolation is FFT, right? FFT is much faster. So normal, like, you know, naive interpolation takes n squared time, which is very slow. FFT is the best interpolation we have is n log square. And we can't have that, then we don't have a system that is actually working in real life. The other thing I need to do is some kind of a zero test, divisibility. Yeah? That is what I said here. I make f, and then you are the verifier. You come to me and say, prove for me that this f actually is 0 at all those points. And that's in mathematics, we do that by dividing this polynomial together. Now, if I go to another ring, and the division doesn't really work like that, then I'm doomed. You know, I need to be able to divide these two objects together to verify that they are 0 at that point. The other thing here you need to do, the verifier challenges the prover on a random point, so they have to evaluate this polynomial at the random point. And that also they use FFT to do it. And if they don't have, then your verifier is very slow. So FFT is essential. The last thing, I'm going fast over this, but after that, you need to do the wiring test. So I verified that the equation is correct, but I had some assumption that these two are equal to each other. So if I don't check that, the prover can cheat and choose two different numbers here, right? So the wiring test is here that these two numbers are, for example, equal. So this is what he needs to check, and that is basically right. So I call this a polynomial as a trace polynomial. I can interpolate it and get a polynomial that at all these places is equal to that value. But then this polynomial should satisfy this, like t of h1, which, for example, come here, it should be equal to t of h2, right? And to do that, a naive way of doing it is basically have a permutation function w that say wh1 is equal h2, and then apply that to this polynomial, and then the polynomial shouldn't move, right? If as place 1 at 2 is the same, then if I move 1 to 2 and then apply the polynomial, it should be the same. And then if I interpolate that and then prove that it's 0 at all places, then I'm done. The problem is this is n squared power, and we don't allow that, right? This is too big. The polynomials of the prover should be of degree n. So a naive way of doing it doesn't work, and you know, at least 50% of Plonk ingenuity was to find a place, find a way of doing it, which doesn't require, like, you know, this blow off degrees here. And that is how it works. We make this function, which that polynomial that's permutated, my polynomial is at the top, and then at the bottom I have a non-permutated polynomial. These obviously, this is wrong, sorry. They are not 1, right? When you permutate them, they are not 1. But if the permutation works, actually, this will cancel with another one somewhere. So what are we going to do here is we are going to multiply these one by one. I make the first this animal for the H1, H2, H3, and I multiply them together. And at the end, when I multiply all of them together, at least they finally should cancel each other. And then I should get 1 at the end when I multiply everything. So I multiply 1 by 1. I add it recursively. And then, you know, this is the recursive equation for it. I add 1, I multiply 1 at each step. And at the end, when I arrive, I should get 1. So to do that, we do this polynomial, right? So I say the polynomial I did was that I get h1. I multiply element with it. This should be hi, I guess. Yeah. So this is hi. Sorry. So if I take hi and go to the next element by multiplying that. Oh no, that is h1. Sorry. This is this x. Yeah. This is basically x. So I multiply this and sorry, Q. And basically I say I make this at every step. I just multiply one h1 into this, and I will go to the next element. I multiply one h1 to this and get to the next element, and I satisfy this recursive thing. And every time I add new element, I add that ratio to it. So Plonk says, if you prove to me that you didn't cheat in constructing this, and at the end it became 1, then the ratio is correct. So what will happen here? The only problem here is the thing that they used here is a cyclic group. If I don't have a cyclic group here, I cannot multiply an element with that. That is something that a lot of other proof system doesn't have. They don't have a cyclic group. But here, I'm using a cyclic group. That is the next thing that Plonk need. It not only using this root of unity just as a root of unity, it uses actually the cyclic group property. So here, basically, I did that, and then I verify. So I will get a very small equation of degree n. I can verify it, but it should be a cyclic group. OK. So for now, we knew what we need. Requirement 1, we need something look like a polynomial, right? We evaluate it at some point, and then I can get the whole function, right? Some kind of a local global condition. I need divisibility. I need to divide one over another. That is how I actually verify that the prover didn't cheat. I need FFT. And FFT is working with the 2 big numbers. So I need to find a way to simulate FFT if I don't have this here. And I need, I need FFT for all this. I have a polynomial. I should be able to evaluate it at endpoints. So I need to be able to interpolate PX. If it's evaluated in endpoint, I should be able to go by. Basically, I need FFT. I'm like, and then, you know, I don't want to solve it in n square. If I solve it in n square, my thing is very slow. So I want to get to something like this. And this is the last requirement, which a lot of systems don't need. Like, you know, even I think Fry doesn't need this. I need a cyclic group because when I do the permutation, then my permutation check is depending on the fact that I have a cyclic group, which make my low degree polynomial check. And you know, if you have an FFT algorithm, doesn't mean that you have a cyclic group. So I need one extra requirement. Okay, so basically the first thing we are going to attack, this is basically a review of ECFFT paper. I'm going to find a way to get a good FFT that I don't have. So here, what I'm going to do, I'm just going to fastly talk about FFT. FFT is basically a linear transform on a function space. This coming from the continuous level, but now we all use it for the discrete version, right? And the discrete version is basically the same. You have function from finite field to another finite field, which is polynomial, right? And FFT, which is Fourier transform, what it does is change the basis. And when it's discrete, then we call it DFT. So an example of this is interpolation, right? Interpolation is just change of basis. So I have this basis, which is the Lagrange basis. If I represent the polynomial on Lagrange basis, I'm represented with the evaluation of the polynomial. If I represent it in coefficient basis, then I'm I'm basically showing it in a normal way that people look at the polynomial. So DFT is basically, you give at endpoint, it gives you a polynomial, you give a polynomial, it gives you the evaluation at endpoint. I said that, so we want to solve it in a faster way. So let's see how FFT works. I'm going very fast over this, but it does some recursion. The big thing here is that every time it wants to evaluate this polynomial, it breaks it into two polynomials, which are strictly less degree, evaluate them, and then add them together. So in the traditional FFT does this, right? And that is where the degree 2 root of unity comes, because every time we take it to power of 2. And then you want to exhaust the space with this power of 2. So I break the polynomial like even powers and odd power. I take one of the x out, and then again I have two polynomial of even power. And then I'm evaluating them. Then I break them again into degree 2 till this is what the even and odd look like. And then now my space is smaller because I took everything to the power of 2. And so half of them be collapsed to the same range. Your range become half size, your polynomial become half size. You try to evaluate there, and you go to the next step. Yeah, so till you get the constant polynomial. You go down to the degree 1, then everything is constant. You evaluate trivially. Okay. So what do we need for this to happen? We need every time that we want to evaluate endpoint, next time should be n half point, and after time n fourth point. So like that, right? So when I take power 2, my domain shrink in the half. That is why we like this power of 2. We need, that is why this should be 2 power of k, because every time I am halving it, right? And then I have a glue step. So after I evaluate this polynomial, so I broke them in a small polynomial, I should be able to glue them easily. And this is the easy glue here, but you might change it and your glue will be different. But this is the naive glue in FFT is this. Okay, so obviously the problem is this. If 2 to the power of k doesn't divide q, then I don't have that thing. So, and we are not free to choose q. So what should we do here? So basically the thing comes here. For example, you choose q for EFQ be pairing friendly. So, and then you don't have a lot of choice for q, and then it won't be FFT friendly. If you want to prove on that q, then you don't get that. That is basically what happened in this. And for example, if you want to prove something on Bitcoin's keys, right? They are in they are in a prime field that has nothing like that. So you cannot use FFT there. So basically here I say, when I want to do FFT, do I really need these roots of unity? And that is the ECFFT paper reply. It says, I don't really need that nice thing. I only need a function that makes my, at every step I need to apply a function that makes my domain half size. I don't even need my domain to become the same. Here, the nice thing about this power of unity is you take power of 2, you go back to the same set. But really you don't, ECFFT paper says you don't need that, right? So only I need this function be easy to compute. Should be 2 to 1, so it kills half of the domain. And then after you do that, you get this polynomial, you should be able to glue them back together. So that is really what we want. We have this field Q, which is a bad field, right? It doesn't have a good power of 2. All I need bunch of 2 to 1 function and a set of that field that every time I apply, it kills half of the domain. And then the function even don't need to be the same. And the D's don't need to be the same, right? So this doesn't show that. But it needs to kill. At the end, you get to one element, and then you can survive. So that is all you need, right? The only problem is we don't have this function like for free, right? Like you look at a finite field, nobody gives you this function, but at least we know one way of finding these functions. And that way of making them is coming through elliptic curve, though at this level, you don't care about the elliptic curve. You only use that function, the elliptic curve, to find those functions, and then you come back to the finite field, and then you just give you this function that kills half of d every time. But that is a way of doing it because other, mathematicians had already worked on it, and they find out how to compute isogeny, the algorithm is there, so why not use it, right? Instead of finding another way of defining this function. So the isogeny is giving us that. So I'm going to give a crash 3-slide course on isogeny just to know what it is. So I'm in FP, right, which is not a good field, and I want to move to elliptic curve, that I make elliptic curve on FP, okay? Elliptic curve is something with this equation, y squared equals x squared of 3, and the points basically x, y, they should satisfy this equation, right? There should be any point on the curve make this equation 0, and then they have this fancy addition law that makes them a group. We don't care what is the detail of addition law. We know that we can add these points together like we add numbers, but in a fancy way. And that makes a abelian group, okay? So what is isogeny? Isogeny is basically a function from this curve, so from the point of this curve that take it to the point of another curve. But this function should have some property, so it should take 0 to 0. And it should be algebraic function, right? It should be expressed by polynomial divided by polynomial. And it should be a group homomorphism. So if you add something, you apply the function to it, it should keep the addition as you add it first and you apply the function, or you apply function add after, it should be the same. So these are the isogenies. So they're a function between elliptic curves, but then we have some good results here. The good result is, if you find a subgroup in this curve, right? I said the point make a group. If you take a subgroup there, you apply the function, you always have a function. You always have a function that's kill all that subgroup. So that is basically what we wanted. We wanted at every level kill 2 elements. Kill 1 element, 2 elements, 1 element. So that theorem in elliptic curve says every time, if you take any elements that you can make a group, then you can find the function that kills that group. It is the kernel. So we are going to use this property to find that function. And this is the size of the degree of the function. Okay. So what is cool about elliptic curves is that we knew that Q is bad and we are doomed. For elliptic curve, there's always a way of finding elliptic curve that has a good value. So that we have this theorem that says if Q is the size of your field, if you're not very, very far from Q, which is the square root of Q, you always find elliptic curve with that number of points. And if you find a number of points that is divide 2 power of n, then you can use those points to do this, to find basically to do the FFT that we talk about. So that is the cool thing about elliptic curve. You have so many elliptic curves over FQ, so you are not limited. But on FQ, you just have no other choice. So now we can find a elliptic curve that has a good power, its group divide a good number, right? So now my Q wasn't good, but I found the elliptic curve that it divide 2 to the power of k divided, okay? And then, so I found this elliptic curve with this number, I will find that. Then I find this subgroup of it that has 2 to the power of k, and then I kill 1 element at the time. And at each level that I kill the element, so I find the element of degree 2 in this group, I kill it, I get one I go one step, right? So I can find phi 1 that kills G prime 0, and I get 1. And then now I have a group with 2 to the power of k minus 1. Again, I find the element that of order 2, and I repeat this, and I find another function. Yeah. So the problem is this isogeny map a curve to another curve, but actually what we needed map between the fields, right? Because we wanted to do FFT on the field. The cool thing about the isogeny is the map actually is just, you see, so this is a map taking a point with x and y coordinate to the new xy coordinate. but the x coordinate is only depending on x. So when I find the isogeny, the first map only depends on, is basically a map between FQ and FQ. So that is how we are lucky here. Basically, I find the isogeny for free. I find a map between FQ, FQ, which we're looking for. Okay. So let's see what algorithm works, and then I will go to the code to look. Actually, this is actually not just, I'm just saying nonsense, actually works. So I find that I start with a FQ that doesn't have 2k through root of unity. I find the elliptic curve on FQ, which has a good 2 to the power of k root of the, element. I find a group of order 2 to the power of k. I start taking the coordinate, so I'll take the coordinate of those, x coordinate of those points. These become element of FQ, and then and then I will find the isogeny, right? And then the isogeny will give me this 2, 2 to 1 function, and I start killing them, and as a result, I will get this, I break the polynomial into 2, and then there's a gluing step that I glue them back together, and I evaluate the polynomial. Okay, I'm going to put this here, and just look at the code for this FFT and all this stuff that I told you. Okay, let me see how can I do it. At 1, I start this, and then 3, 1, 1. Okay, at 1, and then ECFFT, that's right. Okay, you can see it, right? So this is the code. Oh no. Okay. Yeah. Good. I should talk into this. So I don't want to bore you very much, but I go just to the setting at the bottom. So I did this, right? I choose this is my field, is 101, right? So it's a prime number. -1 is 100. So the multiplicative group is, if degree 100, which only divide 4, right? Doesn't divide 8, doesn't divide 16. So basically, the biggest polynomial you can do is degree 3, right? Because with 4 points, you interpolate, you get degree 3 polynomial. I found this elliptic curve, y squared plus x to the power of 3 plus x plus 2. And this one has actually 100 elements. So that one has only 2 adicities, only divide by 4, 2 to the power of 4. Then I'm going into this. Let me look, just print the isogenies, okay? So basically, that is what I'm going to do. I'm going here. I found a cyclic generator. And I kill it here, isogeny builder. So I'm using Sage, right? And I tell Sage, find me the isogeny that kills this point. I find the isogeny. Let's print it, though, every time we make it. Print next isogeny. Okay, so I'm going to start this Sage, PDB. Okay, I forgot that we are doing Python, so sorry. ECFFT Sage. Next, isogeny. I should put in the parentheses. Right, for now it's power of 4, right? So I kill 1, 4 become 2, and kill 2 become 1, so I have 2 functions only. So let's run that. Here, PDB reload. So I'm here, and I'm going to basically call ECFFT, which prints the isogenies, you see? So this is the isogeny, the first one. And this is the second one, which you see the 100 got killed to 50, and then then it goes back to the same curve, but still it kills the second to 50. So the group of size 4 became 2 and then became 1. And then I have my polynomial, which is 1, 1, 1, 1, right? That is what I did.
Sorry, can I ask a question?
Yes.
So the assumption is taking points from one group in the same elliptic curve to another group in the same elliptic curve.
No, it takes it to the different curve, as you see. You see this?
So it's a completely different curve with a different curve equation.
Yeah, it says it here. So the first curve we knew what it was this x plus 2, right?
Right.
And then it took it to 82x plus 30.
Ah, yes. Okay.
The third time I think went back, no, is another curve, 42x.
Okay.
But I'm only caring about the map to FQ, which always become over the same field, right? Because this elliptic curve all define the same field.
Right.
And then I'm looking only what x coordinate goes to what, and x coordinate is coming from the field, so it gives me, even the maps are from different elliptic curves, still give me the same map on each, because the field is the same. I just look at the map over the field and I get the same map.
Right.
So I'm going to run this, and now I'm doing the ECFFT. And basically, you see, I printed at every level that I was evaluating the polynomial. So it takes it down to the degree to polynomial, evaluate that. The second one is I actually interpolate the polynomial using direct. I'm using Lagrangian interpolation just to check that ECFFT gives the same results. At the end, I evaluated at 4 points. That's because I had only 4 points, right? And it shows that they are the same. I can do from a bigger curve, right? So I went to the code and found bigger curves with a bigger adicity. This has 8, 2 to the power of 3, right? And the last one has 2 to the power of 5, which is 32. So I can basically go through the code, and you see this is a polynomial of degree 32 that evaluated on 32 points, and each of them, one of them is happening by ECFFT, and one of them with direct interpolation, just to show that the interpolation has done correctly. Okay, so that solves our FFT problem. Still, we have a cyclical problem. Yes.
One question. So Q is fixed, right? So how difficult or easy it is to find an elliptic curve defined over FQ, given that Q is big, like 256 bits?
Yeah, I understand.
Is also K fixed, like 2 to the K? Is also K fixed or not?
I think so. I mean, you have a lower limit. If you find a curve that is better than that, then that's good.
And algorithmically speaking, given Q and K, how difficult or easy it is to find an elliptic curve?
Yeah, so it's not easy. It's not easy. The small, maybe you want 20, maybe it's easy to find 2 to the power of 10. But then the higher you go, 2 to the power of 20, then become harder.
So let's say Q is like the field characteristic of BLS 12381, and you want K to be 20.
Yeah.
Is it easy or difficult?
So you at that level, you cannot try an error, right? You cannot do random. There is a method. It's called complex multiplication. I don't know if you know it. That's basically give you a way of finding an elliptic curve exactly with the number that you like.
Okay, and the complexity is like feasible?
I think so. It needs some Hilbert polynomial computation, so it takes time. Okay. But it gives you that. I remember I tried that with BLS 381, and I think like I got like I left the computer to compute for 24 hours, and I got to power like 18, but I never got to 20. So the best I found was 18. But now I have a hard time to remember what was the big complexity there that was making it.
The bigger the K, the bigger the circuit you can prove with Plonk, I guess.
Yeah, exactly. You have more criteria. So if you have 1 million criteria, then you only need 20, right? But if you have 20 million, then you have to go higher. So this is the toy example. Obviously, for finding these, I just went over all the elliptic curve existed there, and I found the one that has better, higher thing. Okay, so let me go back to the slide and talk about the last problem, which is the group problem. For now. I like to walk. It's good. Thank you.
Sorry, just for the recording.
Yeah, I know. It's good. That's it. So we got FFT. What else left? Could we do Plonk, which obviously we cannot because I'm going back to the field and there's no cyclic group there. So I need to go to do something else because Plonk doesn't only need FFT, it needs a cyclic group to do the permutation check. So the solution we are going to do here is basically not work in the field anymore, move actually to the elliptic curve and work there. And so I said we need a polynomial, so we have to go some kind of polynomial over elliptic curve, and that's basically called polynomials that are defined over these, points. Before we had a polynomial that univariate polynomials only get x, now it gets points. Okay, so just to see what is the equivalent. So when I'm in the field, a polynomial basically is function from this field to itself, right? And then if I have x is identity function, in elliptic, if you have a bivariate field like x and y, then you get from this field two variable, and then you end up with the same. You map it to the same field. And then if you have elliptic curve, actually you want to take point from the elliptic curve and map it to the field. So I have, this is the concept of my polynomial elliptic curve. So basically they are bivariate polynomial, but we assume that they are only defined where elliptic curve is zero. Where the elliptic curve, when x, y is satisfy elliptic equation. If the point is not an elliptic curve, then my polynomial is not defined. Right, so basically I take the polynomial mod this polynomial. So I take a polynomial from here, but I assume no matter how much from this I add it together, I get the same polynomial. So this is polynomial basically mod basically. So that's what we ended. We get this bivariate polynomial, but we mod it based on that one polynomial, and we get this object with a ring, and we call it coordinate ring of elliptic curve. We call coordinate ring because that is how you define coordinate on the manifold. So they got the name because first there was differential geometry, and then people added algebraic geometry, all the name coming from there. So they are polynomial in this, but then we have this nice theorem. It says any polynomial in this field can be represented like that. A polynomial solely in x, and then another polynomial bx that is multiplied with degree 1 of y, which is obvious, right? If power of y is higher, then you can use this to kill power of y more than 2. So they only need to have one power of y here. So now, instead of making Plonk in a field, I'm going to do it in this ring. That is the question. Is this ring good enough for doing Plonk? So let's look at it. First of all, the degree. So before we had degree of polynomial was the highest power of x, right? But now it's not anymore. So it also makes, so this is the definition of the degree. Maximum twice degree of this, or 2 times degree of bx plus 3. And it's obvious because y is degree 3 and x is degree 2. That is the only thing makes sense. Because you always can take power of 3 of x and replace it with a quadratic power of y. And then if this action will change the degree, then degree is not invariant. So that's the only way you can define degree, is that y has degree 3 and x has degree 2. So we have a new definition of degree in this ring. So can we do interpolation? So in this field we are interpolating. I would give you s point, and it would give me a degree s minus 1 polynomial. Here is different. If I give you s point, then I will get a degree s polynomial. This comes because there is no degree 1 polynomial in the field. There's degree 0, and there's degree 2, 3, 4, 5. So there is no degree 1. As a result, when I need d elements, it gives me degree d. While in this polynomial ring, when I get d elements, it gives me d minus 1. So I have interpolation, but gives me this. The other thing was that the interpolation always works here. Sometimes it doesn't work here. So we have a theorem, and if it doesn't work, then we have to add one more condition to get it work. Like I need to add one more degree, actually. And this is the condition that doesn't work. It's actually the place that we are using. So the naive interpolation doesn't work. Actually, I have to add one more degree. So not only I get degree S, I get degree S plus 1, because this string is not as nice as that string. You know, it gives me this. But it's only 1 degree, so it's not that bad. So naive interpolation, how can I do it? You see, I give you value for fxy, and I want to find me a polynomial with ax plus yb that does that. I mean, the naive way of doing it is basically I write it like this. So I need to find a0 to an and b0 to by, and basically I can get a matrix, right? So you have given me these values, I get this matrix, I want to find these, and these are the setup values. You say at this point it should be equal this, at this point should be equal that. I solve this matrix, right? I get the polynomial, it gets interpolated. The problem is here, right? This is a very bad efficiency. I don't want to do that, I want to do FFT. And now we want to see how can we do FFT. This is from ECFFT2 paper, and that is what they do. So as I said, we found a good curve, right? So I have this cyclic group in it of 2 power of n, and how much do I have? And then I'm adding another point to that. The problem is I cannot work in the group itself. I have to move it away because 0 is in that field. 0 is point at infinity, which is not defined for polynomial. You cannot put point at infinity in a polynomial. So I move the group a bit, so I can give them finite value instead of point at infinity, because polynomial at point at infinity are infinity. They don't give me normal values. So I move it with this h, so I'm getting the element of the group, but I double it, the minus h and plus h. So I get all these points, and I'm going to interpolate it. I get the interpolation values, right? Because they gave me what is the value of the polynomial. And now I add these two together. And if you look at that equation, these two cancel each other. And what left is A. Right? So when I do that, I know the value of A. And then A is a univariate polynomial. So I'm going to use ECFFT to find the polynomial A. Then I use the same ECFFT to find polynomial B. And then I find my polynomial. So I use ECFFT over this double domain, and then I get a polynomial. The only problem here that ECFFT paper doesn't address is that because you doubled the size of evaluation, your degree of polynomial now is doubled. So if you had a 1 million criteria, like you have a degree of 1 million, now you have a degree 2 million. So to improve that, we basically do this. We tell the user, just give me all the criteria on the one of the set, and on the second set, I evaluate only to 0, because I don't know how to evaluate only one set, because I need this criteria to be able to recover A and B. But I say, don't give me here, I evaluate on 0, and then after I evaluate it, so this is now degree 2 million polynomial, right? Then I will get this polynomial that I have evaluated no matter what. You know, because I'm not using FFT, I can evaluate this like with the naive way that I told you, but I have done it before. And then this is a degree 1 million polynomial. I evaluated as 0 at the same point that it was 0. I also evaluated as 0, and then I divide this by this polynomial. So I make an interpolation of degree 2 million, but then I kill 1 million of it at the end. So the interpolation is long, but after that I get a good polynomial. So that's one good thing there. Do we have a 0 test? There is again complication here. In FP you could divide by any polynomial. Here you don't have it because this is not a unique factorization domain. So if you can divide, then it says they have 0 at the same places. But you can't always divide. So the only way you can divide is to make an element that actually has those zeros. So in our case, for example, we want to know our polynomial is 0 here, but I don't have anything that's only 0 here, because I should add the addition of thing that's able to make a function should add up to 0. So I'm basically adding one more point here to be able to do the 0 test. So it's not as nice as before, but it's still doable. So the only thing remaining is that I should be able to do the product check that before I did. So now I don't have a problem. I have a group in elliptic curve, so I have that group. I can make a cyclic group and do all the Plonk stuff. in that group. So now because I got out of the field, now I got the group in an elliptic curve. And I write the same equation, you know, on this. The only problem here is this is not a polynomial. Why? Because polynomials like this, if this was a polynomial, if it was a polynomial, then it has a at infinity is 0, right? At infinity is infinity if it's a polynomial. Now, when I move it with g, it moves the point of infinity. So if I put 0 here, in this, like in this case, let's look at this. If I put 0 here, 0 has moved to g. And at 0, this was infinity. If it was a polynomial, then it will be infinity at here, at g. And something that as g is infinity is not a polynomial. Polynomials are not, they only have infinity at pole. So basically, this because when I add this additional elliptic curve, it gets a denominator. It's not a polynomial anymore. I have to kill those denominators. So my function will get a bit bigger. This is basically what is happening. You get a pole. You want to get rid of the pole. The pole is where the function is equal to 0. So I get all these poles, all these places that this function get to infinity, which is all element of that group G. I multiply to get them. I get the denominator. I multiply the final result with that. Let me go back here. I multiply the final result with that, and I get rid of this. I go 5 minutes on this example, okay? So this is an example. I want to make Plonk, not on the field, but actually on the elliptic curve coordinate ring, right? So the field that I start with is 37, minus 1. It gives you 36, which is only 4. So you only have 2 to the power of 4, right? Then I want to change it to an elliptic curve that give me more place for criteria. So I start with the bad field, which is 37. I find the elliptic curve, which is y to the power of, right? Y squared plus x is to the power of 3 plus x plus 1. Right? This is my elliptic curve. Right? Now it's 48. Now even the field only had 4. Now this is 16 times 3, right? So I have now I have the degree to the power of 4 dividing my curve, right? I get the generator of the curve, right? And I look at the order is 48. I need just the degree 16 group. That is my cyclic group. So I kill, I think, the degree 3. So I will get degree 16 subgroup, right? This is the point. And then this is the coset that, I'm going to generate. So these are the elements of the group, and I use add edge to get rid of the infinity from this group. So this becomes my point. I'm going to interpolate over these points, right? And I define and I have 16 points as a result. I did, so these are the criteria for the Pythagoras, right? I made the matrix, and then I'm just going to solve the matrix to get interpolation. I don't use a ECFFT. So it gives me a polynomial there. You see, this is B, and this is, I guess power of x is 0. So I interpolate each of the polynomial, and then finally this is the polynomial I go out. This is the fx, the gate of the Plonk that is defined over elliptic curve. As you see, some of them has y and some of them doesn't have y, right? For wiring tests, basically, you get into this thing that I told you. Here, I cannot do the wiring test because I don't get a polynomial. As I said, you see, we have this thing from Plonk. We can still use it here, except it doesn't give me a function. So what I need to do, I need to basically multiply with this denominator to get rid of the denominator, and I get a polynomial. Then this is a polynomial. I can interpolate that, and I can do the the check, yeah. So this is the references, basically the ECFFT1 and FFT2, but we extended it to Plonk. Here we have a Kusama ZK summit to invite people to do whatever the ZK they have, just import it to Kusama. Is during the Web3 summit in Berlin if you want to come. We have a, grant and stuff to do it and discuss what can we do there. Thank you very much. Any question? Okay. Okay. You have a microphone, yeah.
So maybe I missed it, but you didn't define the function that goes from E of FQ to FQ. Is that implied?
From E of FQ to FQ, in first case, that I'm not doing Plonk, right? That I will show you. So in that case, but in the second case, when I did Plonk, I never came back to FQ, right?
Oh, so you never go back to FQ?
I mean, somehow I went in an FFT just because I don't know how to do otherwise. But in the first case, so let me show you. 11, 10. So when I do ECFFT, I get lucky with the isogeny. So I guess the answer to your question is really this thing. This is my bridge from EFQ to FQ. Is this theorem that says any isogeny that I'm going to write is of this shape. So phi is working an elliptic curve, but every time that I compute it, the first coordinate is actually function FQ. Right. So I use the algorithm to find the isogeny, and by default it gives me this. So every time I really want to go to FQ, I will use that. This is how ECFFT work, and that is what happened here. And then at the end, when I did this, I needed to do this here. I did another transformation here. So I wanted to interpolate that, which I don't really know how to do it. I used this criteria. So because the y coordinate of this point and this point are negative of each other, and both of them have the same, this will kill this. This part of it, and then I get something only in FQ, which I knew how to do a CFFT, and I find A. Then I will do the negative of that, will kill this one. And I divide by that, and I interpolate this. So these are the two places that I go back to FQ.
Sounds good. Thank you.
Thank you. Thank you very much.
So the projection on the x line of an isogeny always depends on the x coordinate of the point? So not
Only, that's it. There is no y. Yeah, that's it.
So this is only for two isogenies or also for how?
They're for most of isogeny. In degree 2, there might be, like, if your prime is a, if you define over FP2, then it might get complicated. But I'm pretty sure it's more for most isogenies like that.
So if we cannot find a higher to adicity, can we find a smooth field, like powers of other 3, 5, and then mix it or add it?
Yeah, definitely. Yeah, so that's the point. You can use any power you want.
We're sure then that 3 isogenies, 5 isogenies,
have the same shape. Yeah, I'm pretty sure, because I worked on another isogenies. You know, when you want to do hash to curve, you actually use isogenies. If your curve doesn't do a good hash to curve, you use isogeny, you make it to another curve and you bring it back. I did those on BLS 12381.
You talk about Bonnet-Wahhabi paper, I guess.
I guess, yeah, that one. And that is like isogeny degree 17, and it still was look like that. Okay. So I wrote the code in ArcWork, and basically the first function was only only if your prime is like looking crazy, like 2 or 3, then, which we don't work on. I mean, BNS you use as degree 2, but yeah. You're welcome. Thank you very much.